For the next scenario we're going to look at, we have a situation with multiple parts. Okay, so we have a pop gun here, and we're going to take a bullet, and we're going to, or we'll say a projectile, and we're going to compress a spring with it, and then we're going to release it, and we're going to look at its kind of what happens to it at two different positions. We have position B right here, and then position C right here. There is a piece of this that's a little bit tricky because in addition to the spring being compressed, the height of it also changes, which means that when the height changes, the amount of gravitational potential energy changes. And so in this example, they've set height 0 at kind of this equilibrium position for the spring, which means that if here, when we're below height 0, we actually have a negative gravitational potential energy. Okay, so we're going to go ahead, and I've drawn out the LOL chart, and I've actually made it an LOLOL chart because we have 3 snapshots we're looking at. Okay, but the first thing we want to do is just to define our system. So we have the spring here. Okay, so we'll put in the spring. In addition, we have gravitational potential energy. So we'll include the Earth, and finally we'll include the projectile. So our system is the spring, the Earth, the projectile, and now let's go ahead and fill out our bar charts. So to start at position A, if this is position 0 right there, we have actually some negative gravitational potential energy because our height is below equilibrium. And then we're going to have some amount of elastic potential energy, let's say 3 boxes. Okay, and then at the start we have no kinetic energy. Okay, so as we look at this, we kind of have here about 2 total boxes of energy. Okay, because we have 3 plus -1. Now we're going to say it's a closed system, no air resistance, no friction, so no energy will be created or lost. So in each of these bar graphs, there should be 2 boxes of energy. So from position A to position B, you can see that the spring is released and the ball is moved upward, and it's moved upward to position 0, so no longer do we have gravitational potential energy. It's equal to 0, but it actually has increased because we're moving upward. We went from negative to 0, which is an increase. The elastic potential energy has decreased because now the spring is no longer compressed, and it's gone into both getting rid of that negative gravitational potential energy as well as creating kinetic energy, because now that projectile is moving, and so we should have all the remaining energy here as kinetic, so that would be 2 boxes. Finally, when we get to position C, it's actually flown all the way up to its highest point, and so at that point we'll say all that energy has been transformed into gravitational potential energy. There's no more elastic potential energy and no more kinetic energy. So during that last part, kinetic energy has decreased and our gravitational potential energy has increased. Okay, so the next step now is to write out our equation. Okay, that's going to be a 3-part equation, and there'll be 2 equal signs, one here and one here. Okay, I'm not going to, for values where there's 0, I'm not going to put anything, so we can kind of see what the equation will look like. Okay, so I've now written out our equation. At the beginning we have negative potential energy and elastic potential energy. In the middle here we have kinetic energy, and then at the end we have gravitational potential energy. And I just want to point out, we do know what that height is. We do know what this height is. We don't know what K is. We do know what X is. That's how far the spring is stretched or compressed. We know that from right here. And then we don't know how fast it's moving at that equilibrium spot. Okay, so part A asks what the spring constant is, so we want to solve for K right here. In order to do so, we have to compare 2 snapshots that we know a lot of information about. We know everything else about this one, and we know everything about this one. So if we compare these 2, by setting them equal to each other and ignoring this middle piece, we can solve for that spring constant. So let's go ahead and do that here. So I've rewritten this equation so that I'm leaving out the middle piece because we're not using that right now to solve for the spring constant. We'll call this H1 and this H2. So in order to solve for K, the first step will be add this to the other side. And so let's go ahead and do that. We've gone ahead and added that over to the other side, and we can even factor out mg, leaving us with mg times H1 plus H2. So what's happening here is that for potential energy, what matters is how much the height is changed. And so we get the total distance it is away from where it started here. Okay, then we can multiply over 2 and divide by x squared to solve for k. So now to solve for k, we've multiplied by 2 and divided by x squared. Now we can substitute in our values. H1 would be equal to the negative 0.12 meters. H2 would be equal to the 20 meters above that it flies, and then m would be the 35 grams. However, in order to answer this question, we would need our units in kilograms, and so 35 grams would be 0.035 kilograms. Okay, and then finally, x squared is the same distance. It's compressed right here, the 0.12 meters. So the way that we set this up when we talked about the negative potential energy, when we plug in for H1, we want to make sure that we don't put in negative 0.12. We want to put in the 0.12. We accounted for the negative in our bar chart when we said that we had negative potential energy. So go ahead and plug all these into your calculator and see what you get. After punching that all in, you should get that K is equal to about 960 newtons per meter. So that would be how stiff the spring is. It would require 960 newtons to compress it 1 meter. Now we're going to move to the second part of this problem, which asks for the speed of the projectile as it passes through point YB. For this, we're looking at this piece right here, and we can either compare it now to this piece or this piece. Now we can use either one. We know what K is, so we could use all this, or we could use this, and doing this one right here might be a little bit easier because it would just be a much simpler calculation, so that we have 1/2 mv squared is equal to mgh. So now we have just this. We can divide out m. We would use 20 for h, and we can solve for v. I'll let you go ahead and do that part. In addition, this is a question that we can solve using kinematics concepts, because we're going from initial velocity to a final velocity of 0 with an acceleration of 9.8 meters per second squared, causing it to slow to a stop. So you could also solve this using a kinematics equation, but sometimes it could be simpler to use the energy concepts here.